So the midterm, we're not going to ask you to do a question at the level of like a theory question on the homework, because that's probably too hard to do in class in a normal period of time. So, all right, we'll talk more about the midterm next week. Just wanted to make sure you're aware of that, and that you have a homework coming up. And this homework that's assigned, it's due a week after the midterm. So you're going to get a full 3 weeks for the homework that is released this week. Make sure not to completely ignore that until after the midterm, because that'll be a pretty tough week for you. Did you have a question or comment? Okay, yeah. So that's right. The second progress report for the project is due right around then as well. So another reason not to ignore the homework until after the midterm. The midterm, don't stress out about it. It's not going to be a killer midterm. We don't intend to make it a killer midterm. Okay, so we discussed Newton's method last time. I did not get to Quasi-Newton methods. I kind of ran out of time, and I think we're probably not going to go through those. They're not going to be something that you have to implement on the homework, and they're not something you'll be tested on. They are a very useful class of methods, and they have a very kind of, devout following in terms of the people who implement them and try to do everything with Quasi-Newton methods, because they essentially offer you a way to get something that's like the convergence speed of Newton method, but without having to compute the full Hessian and solve a linear system in the full Hessian. They require, I think, some care to work well, but they're an interesting class of methods. They're all based on low-rank approximations to the Hessian. So there's a couple slides here on them. If you're interested, you can read those and then just come to any one of us. We can direct you to more literature on them if you're curious. I wanted just to emphasize this equality constrained Newton's method, because it's something that we're going to be using and reusing in the interior point methods that we talk about today. So we talked at the very end last time, we talked about how to solve an equality constrained problem with Newton's method. And we mentioned that there were various ways to deal with equality constraints. The first two had nothing to do with Newton's method. They were just generic techniques that we could try to eliminate the equality constraints by reparameterizing the problem, right, in terms of the null space of A. That's a general strategy we've gone through at least a couple of times. We could derive the dual. And if we were lucky and knew the conjugate function of f, then we could get a dual that was unconstrained. And we need both in order for this to make sense to know the conjugate of f, and we also need to be able to solve the stationarity condition in x to get a solution for x in terms of the dual variables. So this is not always applicable. This is always applicable, maybe not always a good idea. This is not always applicable. And in many cases, equality constrained Newton is the simplest way to proceed, and it is always applicable when you're talking about Newton's method, that is. And the idea is that when you take a quadratic approximation to the function in terms of its Hessian, and you try to minimize that quadratic to take a Newton update, you actually only take a Newton update in the direction of the feasibility set. So you never leave that equality constraint. So instead of just taking a quadratic approximation to the Hessian, finding its unconstrained minimum, and moving that direction, you take a quadratic approximation to the Hessian, you find its constrained minimum, subject to staying within that equality constraint set, and take a step in that direction. So you never leave the constraint set. Right? So the idea is that you start with some point x0 that satisfies a times x0 equals b. So you start with a feasible point. And then you're going to try to produce update directions, call them v, that satisfy av equals 0. Because when you add some multiple or some scalar constant times v to your current iterate, you're going to stay within the constraint set. Right? Because the amount you're adding under a just contributes 0 to the right-hand side. So in other words, you repeat updates of the form x plus tv, where by construction x satisfies ax equals v, and v is going to satisfy ax equals 0. So x plus is going to also satisfy ax plus equals b. And v is given by minimizing the quadratic approximation you make to your function, subject to the direction you're looking for, which we called z here in this minimization, having the property that az is equal to 0. And if you write down the KKT conditions for this problem, this is minimizing a quadratic in z, subject to an equality constraint on z. We actually did this when we talked about the KKT conditions. Just write down the optimality conditions for this problem. You can see it reduces to solving a single linear system and an expanded set of variables, v and then W. W here is the Lagrange multiplier, or the dual variable that corresponds to this constraint. Okay, so the stationarity condition is just this one. This is the first block of this is the stationarity condition. And the second block is just primal feasibility of the KKT conditions. So go back to the KKT conditions if that part confused you. But in other words, we can always minimize a quadratic subject to equality constraints quite easily. We just do so by solving a little bigger linear system. And that's what the Newton updates look like when we have equality constraints. Any questions about that? No? OK, good. So today we're going to start the first of 2 lectures on interior point methods. Just to motivate them, last time we talked about Newton's method, which applied to twice differentiable convex functions, and repeated updates of this form with step sizes chosen by backtracking. The difference between Newton's method and gradient descent, of course, was that it had a much faster convergence rate. That's what we didn't prove last time. We just kind of stated and discussed the conditions under which that was true. The proof can be found, for the most part, in the Boyd and Vandenberg textbook. And it requires stronger conditions than those that we had for gradient descent, but we get a much faster rate. In terms of epsilon, the convergence rate is log 1 over epsilon. So to get an epsilon suboptimal solution, we need on the order of log 1 over epsilon iterations. We call this a quadratic convergence rate. Now, gradient descent under the same conditions achieves a convergence rate of log of 1 over epsilon. Okay, so it's a whole order of magnitude slower. Another important thing just to emphasize, to point out, this is a local convergence rate. So what we actually saw was that there was a point when you run this algorithm at which it enters what we call the quadratically convergence phase. And once you enter that phase, you only need log 1 over epsilon iterations to get an epsilon suboptimal solution. So we had to kind of start off the algorithm right in order to see this rate in action. But in practice, really, Newton's method, I think, for the most part, it gives you performance that is very different from what you see from first-order methods. So you can really think of this as being representative of its convergence. OK, so what are the downsides of Newton's method? Well, a big downside is that each iteration is very expensive compared to gradient descent methods, because it requires solving a linear system in the Hessian. If the Hessian is dense, that's very expensive. That's on the order of n cubed if you have n variables. Whereas a gradient descent update would cost on the order of n operations. So one way to fix that is to use what's called Quasi-Newton methods, which are less expensive and only approximate the Hessian and solve approximate linear systems in the Hessian. The other downside is that as we've written it, it can only handle equality constraints. So we didn't talk about what happens if you have Newton's method subject to for a problem that is subject to inequality constraints. And that's what we're going to talk about this lecture. That's the motivation for interior point methods, is they allow us to get near performance of Newton, but with inequality constraints. So a broader class of problems. So here's a nice hierarchy to think about. We've worked through various problems so far. And let's consider the specific class of problems that derives from quadratic problems. That's the very basic kind of problem form that we might consider in this hierarchy. It's the most specific. So quadratic problems are very easy. If I give you a convex quadratic problem, all problems here are assumed to be convex, then there's a closed form solution, right? The solution is given by the solution to a linear equation. I just take the gradient of my quadratic, which ends up being a linear function of my variable, set it equal to 0. I solve it. By solving a linear system, I have the solution to my quadratic problem. Okay, this is unconstrained, just minimizing a quadratic. The next level in the hierarchy are equality constrained quadratic problems. So I go from, minimizing 1/2 x transpose qx plus, say, c transpose x over x. The next level in the hierarchy is actually to add equality constraints. Okay, now I'm looking at a broader class of problems. I've just kind of gone up one level. And we actually saw this is really no harder. It's no harder conceptually, maybe a bit harder computationally. All we do is that we solve a bigger linear system. When you write down the KKT conditions for this problem, it requires us to solve a little bigger linear system. One now that's in x, and also in the Lagrange multiplier, or in the whatever you want to call the dual variable for this constraint. Okay, so we get what we call the KKT matrix. We solve a linear system of this form: Q A transpose A 0 times x, and then maybe we call our variable v equals something. And that's how we solve this quadratic, equality-constrained quadratic problem, okay, by solving this bigger linear system and then taking the x component for the solution. That was the next level of the hierarchy. So Newton's method extends on these. So Newton's method takes into account the fact that solving equality-constrained quadratic problems is very easy. We can do it in closed form. And it extends on this by offering us to switch out the criterion with some arbitrary doubly smooth function of x. Okay, so we're going to swap out this quadratic with f of x. And what Newton's method does at a high level, if you recall, is it iteratively approximates f of x with a quadratic. So at every iteration, Newton's method has us solve this problem, which we can do easily. And it uses those, it pieces together solutions to that problem to get a solution to this problem, the criterion swapped out with f of x. Okay, so it knows that solving a minimization problem of an arbitrary doubly smooth function subject to equality constraints is hard. So it transforms that into an easy problem, which iteratively solves quadratics, minimizes quadratics subject to equality constraints. This was Newton. So we've already traversed this part of the hierarchy. Now we're going one step up. We're looking at what we call interior point methods, which are built on top of Newton's method. Okay, and the problem class they consider is what happens when we add inequality constraints. So maybe hi of x is less than or equal to 0, I equals 1 through m. And what they do is that they transform a problem of this form to a problem of this form. So back to minimizing some arbitrary doubly smooth function subject to equality constraints, and allow us to then perform Newton's method. So every solver that we've seen kind of transforms the problem in question into one that's one level down in the hierarchy, so because we know how to solve it. Okay, so here what are we going to do? We're going to replace f by a quadratic iteratively. And here we're going to replace hi by smooth functions in the criterion. So we're going to alter the criterion, approximating these inequality constraints by smooth functions. And now we have the minimization of a smooth function subject to equality constraints without any inequality constraints, and we just apply Newton. And we do that repeatedly. So each of these we do repeatedly. So that's the hierarchy to keep in mind. Interior point methods are built on top of Newton's method, which is built on top of quadratic, equality-constrained quadratic problems. So let's get specific, and let's consider a convex problem, right, of our generic form. We have constraints hi of x less than or equal to 0, equality constraints ax equals b, and a criterion f. And we're going to assume that all of these functions are convex and twice differentiable. Okay, it's kind of like the basic thing we will assume for applying what we call the log barrier method. It's our first interior point method we're going to learn. The first thing that we do when we see this problem is we're going to define what we call a log barrier function that pertains to its constraints, its inequality constraints. And we're going to denote it by phi of x. And it's going to be given by minus the sum over all I of log of minus hi of x. Okay, so the minus signs may look a bit startling, but it's easy to remember whether they should be there. Log cannot be evaluated at a negative argument, right? That would not make any sense. And the constraint is that hi of x is less than or equal to 0, so we have to place a minus I in here. And we're going to want to place a penalty on points x that don't achieve Right. So we're going to want to, if we didn't have the minus sign, then you'll see that when what we're doing is approximating indicator function, and it will be giving us the wrong direction of approximation. So let me hold off on the outer minus sign for now, and just the picture I show you in the next slide is going to explain its role. I think it's easier just to see pictorially. But this is called the log barrier function for the above problem. So if I have constraint functions hi of x, I take the log of the negative hi of x, I sum them up, and I take the negative of that entire quantity. It's called the log barrier function. And its domain is a set of points x that are strictly feasible. So this makes sense as long as x satisfies all these inequality constraints strictly. Okay, so I think it's a lot easier just to see pictorially the approximation that this barrier function, log barrier function, provides to the indicator function. We can think about rewriting our problem. So forget about the equality constraints for now. Just write our problem as minimize f of x plus a sum of indicator functions. And each indicator is the indicator that hi of x is less than or equal to 0. That's equivalent to having those constraints. Right? This will give us 0 if hi of x is less than or equal to 0, and infinity otherwise. It's equivalent to placing those constraints on our problem. What I've drawn here is the indicator function that x is less than or equal to 0. Or I guess this is u. U is less than or equal to 0. Okay? That's this dotted line. It's 0 when u is less than or equal to 0, and it's infinite as soon as u is bigger than 0. What each of these curved lines represents, each of these curves, is one of the family of functions minus log of minus u times 1 over t. Okay? And as I make t larger and larger, this smooth log barrier approximates the indicator function. It provides me with a smooth approximation to the indicator function. You can see that because log, as the argument inside the log approaches 0, it approaches infinity extremely fast. Okay, so as I get close to the boundary of the constraint set, the log function would approach minus infinity. So the negative log would approach infinity, just like I want for the indicator function. That was the right direction I was talking about. And log grows to infinity very slowly as its argument grows to infinity. And so if I multiply it by 1 over t, I'm degrading its slope more and more. So I'm making it grow, in this case, to minus infinity slower and slower because I've taken the minus log. So 1 over a million times log of minus u is going to look pretty close to the indicator function that u is less than or equal to 0. Okay, and 1 over 10 million is going to look closer, etc. So as I drive that barrier parameter t larger, I get a smoother. I always have a smooth approximation to the indicator function, but I get a closer and closer approximation. Okay, so now you can kind of guess what we're going to do. We're going to have a problem of this form, hard to solve because these are hard inequality constraints. We're going to replace them by a term in the objective that looks like this, where t is a large number, okay, because the larger the better the approximation. And we're going to solve this smooth problem without inequality constraints. And we're going to claim that provides us an approximation to the inequality constraint problem. Any questions before we move on? Because that's kind of a crucial step here. No? Okay. So let's get started with a central path. So it helps to write down a few properties of this log barrier function, just to have kind of at hand when we start talking about Newton's method that uses the barrierized criterion. And we'll just keep these kind of, like I said, aside for later, but let's just derive them now. This log barrier function is a function that goes from Rn to R. So x is like our optimization variable. It's generically, say, n-dimensional. So we're going to want to write down its gradient and its Hessian for when we would be applying Newton's method to the criterion that's approximated the indicator function by this barrier term. And I've just given you the answers. They come from just using the chain rule. So if any of this is unclear, then sit down with a pad of paper and go through the steps of the chain rule. But you can think about, first of all, the sum doesn't matter, right? Just think about the gradient of this function, minus log of minus hi of x for each I, and then just apply the sum at the end. So the chain rule tells me that this is equal to 1 over minus hi of x, but then I have a minus sign on the outside, times the gradient of what's in the inside, and that's going to give me minus the gradient of hi of x. And so summing that up, I get, this is the gradient of phi. It's just the sum from I equals 1 to m of 1 over hi of x times the gradient of hi of x, and then a minus sign, a leading minus sign, because there was a total of 3 minus signs. And the Hessian I get just from computing the derivative of this quantity. And this is just a product rule. For example, if I take the first I take the derivative with respect to this quantity, I get minus 1 over hi of x squared times the gradient of hi times the gradient of hi transpose. That's the first term in the product rule. And if I now take the derivative of this term, I just get the Hessian of hi of x times minus 1 over hi of x. So summed up, this is the final Hessian. Okay, so that was just kind of like a verbal walkthrough, but these are the quantities that we're going to need to apply Newton's method to the criterion that's replaced indicators with the barrier function, the log barrier function. Okay, gradient and Hessian of the log barrier function. So let's talk about what we call the central path. And we're going to get a conceptual understanding of what the log barrier function does for us, and then we're going to get into algorithms right after that. So the problem to consider is what happens when I replaced the hard inequality constraints with my smooth log barrier term. And initially I had this multiplied by 1 over t. I just moved the t to the criterion for no reason. It's just maybe for simplicity. So I multiplied the whole criterion over t. So the role of t is the same here. As I make t larger, the barrier function has less and less importance away from the boundary of the constraint set. Okay, so it's the same problem, just I've put t multiplying the original criterion function rather than 1 over t multiplying the barrier function. The central path is defined as the solution to this problem as a function of t. So for every t I could solve this problem, call the solution x star, and now I'm looking at how x star behaves as a function of t. That's what we call, in the context of barrier method, the central path. And for every t, we can characterize the solutions to this problem via the KKT conditions. Let's write on the KKT conditions for this problem and figure out what it means for x star of t to be optimal, what it means for x star of t to lie on the central path. The first are just the primal feasibility constraints that I get, right? The equality constraints and inequality constraints. And I only have one dual variable here that's corresponding to this equality constraint. That's what I call w. No constraints in the sign of w because it's an equality constraint. So the only other part of the KKT conditions is stationarity, and that's given here. It's saying that if I take the gradient of this, if I take the Lagrangian, right, that's the Lagrangian. And if I take the gradient with respect to x, and I set it equal to 0, then that gives me the stationarity condition. Gradient here because all functions are convex and smooth, right? That's why we're using the gradient. And the gradient of the first term is just grad f. The gradient of the second term, well, we already computed that, right? That's what I get by taking the sum of minus 1 over hi of x times the gradient of hi of x. And the last term, I just get a transpose w from taking the gradient of that. Okay, so if I can solve this problem for some w, then I have characterized a solution on the central path for that particular value of t. And the hope is that as I drive t to infinity, as I make t larger and larger, the solutions that are characterized by these KKT conditions, they approach the solution to my original problem. Let's call it x star. That was at least the motivation, right? I multiplied the barrier function by 1 over t, and as I made t larger and larger, it approximated the indicator. So hopefully the solutions to its problem approach the solution to the original problem as I drive t to infinity. So a very important example, this is actually how all of these methods were developed first in the context of linear programs. And I'm going to talk about some history of their application to linear programs next time. But a very important example is the log barrier problem version of a linear program. Okay, so here I've taken an LP. I've actually got rid of the equality constraint. So just assume that I have an LP that's given by minimize C transpose X subject to these constraints. Some matrix D times X is less than or equal to epsilon, E. This is what the barrier term looks like for those constraints. Right? So I rewrite this as DI transpose X is less than or equal to EI, or minus EI is less than or equal to 0. And I add minus the sum of log of the negative constraint functions, which is, in this case, just EI minus DI transpose X. So if I were to solve this problem for a particular value of t, make t larger, solve it again, make t larger, solve it again, make t larger, solve it again, my hope is that I'm going to approach the solution to my linear program. And this is a this is a nice picture from the Boyd and Vandenberg textbook. I'm going to blow it up a bit. So what this is showing you is this is the constraint set to my LP. This is the polyhedron given by dx is less than or equal to some vector e. And this is the central path. So here I've solved the problem with t pretty much equal to 0, some very small value of t. And I've made t larger and larger and larger. And as I make t larger, you can see, indeed, I am approaching the solution to my LP, which I know must lie at an extreme point of my polyhedron, from what we know about linear programs. So I'm going to have to lie eventually at an extreme point of my polyhedron, and it approaches it in a smooth fashion. So this was the solution at t equals 10. Maybe this is the solution at t equals 100, t equals 1,000, etc. We eventually approach the solution to the LP. So we can interpret the stationarity condition succinctly for linear programs. So in the context of the central path, we often call the stationarity condition that I wrote down on the last slide the centrality condition. It's what puts the point on the central path. So it's called the centrality condition sometimes. But when I take the gradient of this Lagrangian, when f is just C transpose x, and phi is the barrier function that corresponds to this constraint here, dx less than or equal to epsilon, what I get for the centrality condition is this. T times c must be equal to 1 over EI minus DI transpose X times DI. And what that tells us is that the gradient, right, this is the gradient of the barrier function. It must be parallel, right? It must be parallel to minus c. I move tc the other side. So I have the gradient is equal to some constant times minus c, which means that if I were to look at the hyperplane to the set of all c such that C transpose X is equal to C transpose X star, then the hyperplane that lies tangent to this set this hyperplane is itself tangent to the contour of my log barrier function at X star. So the best way to see that is just to look at the picture. So here are the contours of phi. Each of these dotted lines give you contours of the log barrier function phi as I make t larger and larger. And if I go to the point x star, and I go to the, if I were to look at, for example, the normal vector that lies normal to the tangent at the point x star, to this contour, that points in the direction of the negative gradient of the loss. So this points in the direction of minus c. That's true at every point. Okay, so it's a nice interpretation of the centrality condition. It's telling you that, being on the contour, I want to be maximally aligned with the negative gradient of the loss function for an LP. Okay, and even just looking at the contours of phi, I think actually are quite, it's quite intuitive here. You can see as I make t larger, maybe I'm plotting, say, I'm always plotting the 90th% contour of my function phi. It's going to approximate the polyhedron in question. It's another way of seeing that the log barrier function itself better approximates the indicator function by looking at its contours. Okay, so we're going to see that we can get dual points from the central path. And this is going to be a very useful fact because we're going to use it to derive a duality gap that's going to play a very important role in our algorithm that we'll derive in just a few slides. So for now, we're just going to go through the fact that if you ever solve the problem, the log barrier problem, at some value of t, and so you have a point on the central path, we could define dual variables that are feasible for our original problem in question. Not the barrier problem, but the original problem in question, right from the central path. It's a very useful fact. So in fact, let me just define, remind ourselves. This was our original problem. So to get dual variables for this problem, I need a ui for every inequality constraint and a vi for every equality constraint. Okay? How am I going to define those from a solution on the central path? I can define ui just to be minus 1 over t times the achieved value of the criterion in the ith function, hi of x. And I'm going to define v to be equal to w over t. W was the solution that I had when I solved the KKT conditions for the barrier problem. So I'm just saying that from these KKT conditions, which apply to this barrier problem, we can actually derive feasible dual points for our original problem, the one that did not replace the indicator by phi. And this is how we're going to do it. U is going to be equal to minus 1 over t times hi, and v is going to be equal to w over t. Why are these feasible for the original problem? Well, we can see that pretty easily. First of all, each component of ui is strictly positive because each component of hi is strictly negative. Right? This came from the primal feasibility condition for our barrier problem. And the more important one is that this lies in the domain of the Lagrange dual function. Right? We have to actually check that this point itself lies in the domain of our Lagrange dual function in order for this to be feasible, because remember, when we form the Lagrange dual function, it gives us some implicit constraints from its domain. And we can check that by seeing that it actually minimizes the Lagrangian at the point x star. So if I were to minimize the Lagrangian over x, at x star, we see that that's the minimum if we plug in u star and v star to the Lagrangian. And that just comes right from the stationarity condition. So this is kind of so straightforward that it's confusing, I think. So let me just write them down. This is the stationarity condition that we solved. That's the stationarity condition that we solved from the central path problem. We're assuming we have a solution x star and a dual solution w that satisfy this. I'm just going to divide through by t everywhere. And now you can see all that we've done is we said, hey, this looks a lot like the stationarity condition for our original problem, right? If I defined this to be ui and this to be v, then this looks like the stationarity condition for our original problem. That's all we've done. Okay, so we've said that with these definitions of dual variables, we have feasible dual points for our original problem. Questions? Why don't we have optimal points for our original problem? What have I not met? So I have the stationarity condition satisfied for our original problem. I have primal and dual feasibility. Right, so complementary slackness is not met for our original problem. Very important, right? In fact, what do we have in place of complementary slackness? So we should have ui times hi of x is equal to 0. What do we have instead here? By definition of ui. Yeah, it's actually, as we defined it, minus 1 over t. So it's very close to 0 if we make t bigger. Another kind of insight that you can keep in mind, that as we make t bigger, we're kind of approximating the KKT conditions for our original problem. So the reason that we don't actually have solutions to the original problem at any particular value of t, even though we've solved the log barrier problem, is because we haven't met complementary slackness. Okay, but it's very useful nonetheless, because this allows us to bound at any point how suboptimal we are on the central path as a function of t. And we're just going to compute the duality gap. That's all we're going to do. So I'm going to compute the Lagrange dual function at the point u star v star. I'm going to compute the difference between f star and that Lagrange dual function g, evaluate at u star v star. And that's going to be our valid duality gap. And just plugging this in, right, I already told you from this expression here that by construction, the Lagrange dual function at u star v star is just the Lagrangian itself, right? This is what this condition is telling us. It's telling us that x star minimizes the Lagrangian at u star v star. So now I'm just evaluating the dual function, which is the Lagrangian. And that's just by construction, right? F at the point x times the sum of ui times hi of x plus v transpose ax minus b. And this part right here is equal to 0, because ax star is always equal to b on the central path. That's one of the equality constraints that we meet. This, by construction, by the way we've defined ui, is equal to minus 1 over t summed up m times, right? Because their product is minus 1 over t, by the way I've defined it here. And so the total of this sum is minus m over t. In other words, we've shown that the difference between where we are on the central path and optimality is at most m over t, right? We've shown that f of x star of t minus f star, sorry, first we've shown that if I take these feasible dual points, this is less than or equal to m over t, and that implies, we know that implies from our study of duality, that the suboptimality is bounded also by m over t. So this is actually maybe the closest to a formal proof we have so far that the barrier method works. It's telling us that if we ever were to solve the barrier problem at some value of the parameter t, then the distance we are from suboptimality in terms of the criterion achieved is less than or equal to m over t. So if I make t arbitrarily large, I get arbitrarily close to the optimal criterion value. So our hope that this strategy makes sense is going to work. It looks like formally it's going to work. Okay. So let's go through just this one slide, and then we'll take a break and talk about an algorithm that we're going to put forward to actually solve the original problem from a sequence of barrier problems. So another way you can interpret the central path is via what we call the perturbed KKT conditions. And this is, in fact, what we already kind of said verbally, but I wanted to write them down because our second interior point method that we study next time, which is called the primal dual interior point method, it's derived entirely from the perspective of the perturbed KKT conditions. Okay, so this is going to be very important for our next interior point method. We already saw that we can think of the central path and the corresponding dual points as in the following way. They solve the stationarity condition. Okay, that was right here, as I've defined them. They solve UI. They satisfy UI is bigger than or equal to 0, and they satisfy the primal constraints. By construction, I have that hi of x is less than 0 and ax is equal to b. So that has almost everything satisfied with the KKT conditions, except for complementary slackness. And instead of having the true product of ui and hi being equal to 0, as we do in the actual KKT conditions for original problem, by construction, we have their product equal to minus 1 over t. That's how we've defined them. So you can think about, instead of an equivalent way of thinking about it, if you forget about the log barrier function entirely, forget about the idea that it approximates the indicator function, and it gets better and better as t gets bigger and bigger, you can think about this instead, another way of thinking about it. What I've done is I've taken the KKT conditions and I've replaced complementary slackness with something where I have minus 1 over t on the right-hand side. And I've solved this problem. And then I've made t bigger. And I solved this problem, etc. So I am trying to satisfy feasibility and stationarity exactly and approximately satisfy complementary slackness and make that approximation tighter and tighter as t gets bigger and bigger. Okay, these are two ways of viewing the same idea. Perturbed KKT conditions in the log barrier function. Any questions about that? Yeah. Right. So that's a good question. So I've also kind of swept something under the rug with you guys here, which is that I put a strict inequality here in these conditions rather than a non-strict inequality. That was because the domain of the log barrier function, so I've actually intersected these KKT conditions with the domain of the log barrier function, right? Because the domain is only points for which hi of x is strictly less than 0. Is that related to complementary slackness? I don't see it as being necessarily related, but I could be missing your interpretation. The approximation to complementary slackness is, I mean, that comes from the way that we've defined these dual feasible points. But I guess it is indirectly related because what we've done is we've approximated the hard constraint with a smooth function that approximates it. And we've attributed that part of the stationarity condition just to a dual multiplier. Yeah, we'll see more about the perturbed KKT conditions next time because those are the jumping point for the primal dual interior point method. For the log barrier method, mostly, I think the way that most people remember it, and the way that I certainly remember it, is with this picture in mind. You're trying to approximate a very non-smooth function, which is the indicator with something that's smooth, so you can apply Newton's method. Any other questions? Yeah. So,
because here you have a solution on the boundary.
Right, but why would, I mean?
Well, I know in this case it's a linear program, so the solution goes on the boundary.
So you're asking if I didn't have a linear criterion?
I guess, yeah.
Yeah, I don't see any reason why that has to, why the solution has to lie in the boundary of the constraint set in order for the barrier method to converge. If the solution was inside the constraint set strictly, then that would probably be a more favorable case for the barrier method because you would not have to drive t as large because all the hi's of x's would stay away from 0. So you never get to the case where the log barrier was very steep. So I think it would still work fine. But yeah, as you mentioned, for a linear program, it's always going to lie in the boundary. So this is going to be always the picture you can keep in mind. That suppose I'm drawing the 95th percent contour of phi. As I make t larger, that smooth version of the boundary starts approximating the boundary better and better. Other questions? Let's take a break, and then I'll describe the actual algorithm when we get back.